Welcome. This video is a presentation of 4 points of concurrency for a triangle. These points are the orthocenter, found by the intersection of the altitudes, the centroid, found by the intersection of the median lines, the circumcenter, found by the intersection of the perpendicular bisectors, and the incenter, found by the intersection of the angle bisectors. Prior to finding these points for any triangle, let's cover a few basic concepts. First, the closest distance of a point to a line is the perpendicular. The shortest distance between the points A and the line L is along the blue line. The distance between the point and the line L is longer using the orange line. The line segment drawn which is not perpendicular is clearly longer than the line segment drawn which is perpendicular. You can confirm this by inspection. Since the perpendicular line is unique, it is useful as a reference point when we talk about this shortest line from a vertex of a triangle to the opposite side. We call it the altitude. Second, a bisector cuts something into 2 equal pieces. Line segments can be cut in half, and so can angles. A line segment is on the left, and an angle is on the right. Look at the black line L on the left, cut by the dark red line at the red dot. The red dot is exactly in the middle of the line L. This cuts L into 2 equal pieces. The part of L on each side of that red dot has the same length. The angles can be cut in half too, as seen in the black angle A, shown by the black arc on the right. The yellow dashed line is the angle bisector and cuts angle A exactly in half. This means that the angles marked by the orange arcs to each side of the yellow dashed line are the same. The first point of concurrency we'll consider is that found by drawing the altitudes. Let's take the triangle shown with sides A, B, and C. Angles and vertices are opposite to each other, which are labeled as A, B, and C. Points are put on the vertices just to help form a clear picture for the vertices. We don't care about what kind of triangle. The triangle could be obtuse, acute, or right. It could be green or blue for all we care. We now want to draw the shortest line from a vertex to its opposite side. The altitude means height. When we find an altitude, we find a triangle's height. Let's draw the shortest line from the point B to the line AC. The only way to draw the shortest line from vertex B to side B is to extend line B further to the left, shown by the dashed green line. The perpendicular line dropped from vertex B to the extended side B is shown by the dashed blue line. This perpendicular is given the special name altitude. We can see that the altitude is not always inside of the triangle. The same triangle is shown 3 times. The altitude from each vertex to the opposite side is shown by the dashed blue line. Notice that in this case, 2 of the altitudes are outside of the triangle. However, there is no requirement for this to be the case, as one of them is inside the triangle. If the altitudes are extended, they will all intersect in a single point. The point where the altitudes intersect is called the orthocenter. The orthocenter is one of the points of concurrency. There is nothing particular to note about the orthocenter except its relationship to 2 other points of concurrency. That is, the orthocenter, centroid, and circumcenter will be seen to fall on the same line. The second thing we'll look at is a thing called a median line of a triangle. When the word median is used for a triangle, think about the word middle. A line segment drawn from a vertex to the midpoint, middle, of its opposite side is called a median line. Let's produce the median from the vertex A to the side A. First, put a mark exactly in the middle of side A. Let's label this point M for middle so it's easy to remember. Thus, point M is halfway between points B and C, as can be seen. Alternately, we can say the distance BM is the same as CM. Next, we draw a line segment from the vertex at point A to the midpoint, point M. This line segment AM is called the median line. The same triangle is shown 3 times. The midpoint between each side is marked with a point, and then the median line is drawn from that point to the vertex opposite it. The median line for each vertex is shown by the orange line. The median for vertex A is drawn from vertex A to the middle of side A. The median for vertex B is drawn from vertex B to the middle of side B. The median for vertex C is drawn from the vertex C to the middle of side C. The median lines are always inside the triangle. The 3 medians of a triangle always intersect in a single point. This point is called the centroid. The centroid is the center of gravity, the center upon which the whole triangle is balanced. A pin that is placed at the centroid will balance a triangle where it can remain stable from tipping over or falling off. The centroid is always inside the triangle. The third thing we can do is bisect a side and draw a perpendicular line. Once again, the middle of a side is found, then a perpendicular line is drawn. This perpendicular bisector is shown by the blue dashed line for side B. In this case, we do not care about the vertices of the triangle, only the sides. Find the middle of the side and make a perpendicular line. The same triangle is reproduced, but the perpendicular bisector is drawn for a different side, side A. The same triangle is reproduced again, and the perpendicular bisector is drawn on the third side, side C. The 3 perpendicular bisectors will all intersect in the same point shown by the red dot, which is labeled the circumcenter. As stated earlier, the 3 points of the orthocenter found by the altitudes, of the centroid found by median lines, and of the circumcenter found by perpendicular bisectors all lie on the same line. This diagram shows the 3 points of concurrency that we've already looked at. The orthocenter, light blue, the centroid, dark blue, and the circumcenter, red, all lie on the same line here shown as a glowing double purple line. The double purple line is called the Euler line. The colors of the points have been left the same as when they were developed earlier. Note that no proof of this relationship is being given, but rather the fact alone is presented. One more point of concurrency commonly presented in schools, but not on the Euler line, is the incircle. The incircle is found by the angle bisectors. The angle shown at vertex A is bisected by the goldish line. Note that this line does not necessarily bisect the line segment BC, and is thus different than the median line, except in special situations. The angle A is bisected and is the only thing used to form the angle bisector. The same triangle is reproduced. This time, the angle at vertex C is cut by the angle bisector. The same triangle is reproduced again, but here the angle B is bisected by the gold line. The angle bisectors of a triangle will all intersect each other at the same point. This intersection is called the incenter and is shown by the green dot. The incenter is important for the fact that it is the center of the biggest circle that will just fit inside of the triangle. Hence, the intersection of the angle bisectors is always inside the triangle. Now that the 4 points of concurrency have been shown, let's diagram an interesting fact about 2 of these points. The incenter is the center of the largest circle that will just fit inside the triangle, barely touching each side of the triangle at one point. See the green circle shown in the triangle. The next interesting fact is seen for the circumcenter. The circumcenter is the center of the circle that circumscribes the triangle, which means that each of the vertices of the triangle lie on the circumference of a single circle shown here in red. And that's it for this presentation. Please let me know what you think. Please let Outshine Tutoring know how we can help you, and leave your comments below.